By stability we mean the tendency of airplane to return to its equilibrium position after it has been disturbed. So, an airplane must have sufficient stability that the pilot doesn't become fatigued by constantly having to control the airplane because of external disturbances. We have two conditions. Two conditions are necessary for an airplane to fly its mission successfully. First, the airplane must be able to achieve equilibrium flight. Second, it must have the capability to maneuver for a wide range of flight velocities and altitudes. To achieve equilibrium or perform maneuvers, the airplane must have equipped with aerodynamic and propulsive controls. The design and performance of such control systems is an integral part of airplane stability and control. The stability and control characteristics of an airplane are referred to as the vehicle's handling, or we may say flying qualities. So it's called handling or flying qualities. An airplane will be considered of poor design if it is difficult to handle regardless, irrespective of how outstanding the airplane's performance might be. So, please differentiate between performance and flying qualities. Therefore, in the study of airplane stability and control, we are interested in what makes an airplane stable, how to design the control systems, and what conditions are necessary for good handling. We have to know that stability is a property of an equilibrium state. So, to discuss stability, we must first define what is meant by equilibrium. The airplane is said to be in an equilibrium state when the resultant force and the resultant moment about the center of gravity both be equal to zero. When forces and moments are not zero, the airplane will be subjected to translational or rotational accelerations. The subject of airplane stability is generally divided into static and dynamic stability. Static stability is the initial tendency of the vehicle to return to its equilibrium state after a disturbance. Please take care of the word initial. It is the initial tendency to return the vehicle to its equilibrium position, no matter it succeeded or not, to rest again at this equilibrium state. So, if the airplane is disturbed, the question is, what is the immediate response after disturbance? Will it start to go back in the direction of equilibrium? If the answer is, then the airplane is statically stable. Let's imagine a ball stays at rest on a curved surface, like that one in figure A. If the ball is subjected to any disturbance, the gravitational attraction will pull it towards its initial equilibrium position. We call this equilibrium as a stable equilibrium point. While in figure B, if we were able to balance the ball on curved surface, then any displacement from that equilibrium point will cause the ball to roll off the surface. This equilibrium point is unstable. That's why we stated previously that stability is just a property of an equilibrium state. Let's look at figure C. As we can see, the ball is placed on a flat plate. If the ball were to be displaced from its original equilibrium position, it would remain at the new position. This would be classified as a neutrally stable equilibrium point. This is the boundary between stability and instability. From this overview, we can realize that static stability has various types. We may have a stable equilibrium point, or in case of instability, we have an unstable equilibrium point, and neutral stability, which is to have a neutrally stable equilibrium point. While in static stability we were talking about the initial tendency of the airplane to return back to its original equilibrium point after being disturbed, in the study of dynamic stability we are concerned with the time history of the motion of the vehicle after it is disturbed from its equilibrium point. By studying these graphs, please note that these scenarios are all statically stable as they have the initial tendency to move to equilibrium point. But as we can see, we have several airplane motions that could occur if the airplane were disturbed from its initial condition. As to the figure on the left, the reduction of the disturbance with time indicates that there is a resistance to the motion and therefore energy is being dissipated. The dissipation of energy is called positive damping. This is the case of dynamic stability. This is the case of dynamic stability. Positive damping for an airplane is provided by forces and moments that arise due to the airplane's motion. In positive damping, these forces and moments will oppose the motion of the airplane and cause the disturbance to damp out with time, as we can see in the left figure. As to the right figure, if energy is being added to the system, then we have a negative damping. An airplane that has negative damping will be dynamically unstable. So this is the case of dynamic instability. The middle figure shows zero damping, and hence this is the border between dynamic stability and dynamic instability. Dynamic stability is usually specified by the time it takes a disturbance to be damped to half of its initial amplitude. In the case of an unstable motion, it is specified by the time it takes for the initial amplitude of the disturbance to double. In the case of an oscillatory motion, the frequency and period of the motion are extremely important. To conclude the issue of stability, please note that the vehicle can be statically stable but dynamically unstable. Static stability, therefore, doesn't guarantee dynamic stability. However, for the vehicle to be dynamically stable, it must be statically stable. The condition of static stability for an airplane is the same, like the previous example of the ball swinging on a curved surface. Again, we have to have a restoring moment when the airplane disturbed from its equilibrium position. Let's consider the two pitching moment curves of the two different airplanes. Airplane 1 and airplane 2. Suppose that both airplanes are flying at the equilibrium point denoted by B. At this point, Cm equals 0. Hence, the airplane is not subjected to any moment. We also call this point as a trim point. So in flight mechanics, the word equilibrium is equivalent to trim. If the two airplanes suddenly encounter an upward gust such that the angle of attack is increased to point C, airplane 1 will develop a negative pitching moment that would tend to rotate the airplane back to its trim point. However, for the same disturbance, airplane 2 will develop a positive pitching moment that will tend the aircraft away from the equilibrium point. On the basis of this analysis, we can conclude that to have static longitudinal stability, the aircraft pitching moment curve must have a negative slope through the equilibrium point. Therefore, Cm alpha, which is dCm by d alpha, should be less than 0.
If we look at the pitching moment curves of two airplanes that satisfy the previous condition of static stability, we can notice that both curves have negative slopes. So Cm alpha, which is equal to dCm by d alpha, is less than 0. But what about the trim condition? As we know, the trim, which is the state of equilibrium, means that the airplane is not subjected to any moment. This happens when Cm equals 0. As we can see, airplane 1 can be trimmed at a positive angle of attack. While airplane 2 can be trimmed only at a negative angle of attack. Now, the question is how the airplane can generate enough lift to carry its weight with a negative angle of attack. So, airplane 2 can't generate such lift at its equilibrium point, while airplane 1 can do. Therefore, in addition to have static stability, we must have a positive intercept, that is Cm naught greater than 0, to trim at a positive angle of attack. If you have a negative intercept in the pitching moment curve, you can't satisfy such condition.
The two conditions of airplane longitudinal static stability are: first, the airplane should have a negative slope of Cm versus alpha curve in order to restore the airplane to its equilibrium point if subjected to any external disturbance. Second, the pitching moment versus alpha curve should have a positive intercept. It means Cm naught should be greater than 0. This is to enable the airplane to trim at a positive angle of attack to enable the aircraft to generate enough lift to carry its weight. If we have pitching moment versus coefficient of lift curve instead of pitching moment versus alpha, The criterion of longitudinal static stability can be reached as follows. By definition, Cm alpha is dCm by d alpha. It can be extracted to dCm by dC alpha times dCl by d alpha. But look at this term. dCl by d alpha is the slope of the coefficient of left versus alpha curve. This term is always positive quantity. So, in order to have a negative Cm alpha, we have to have a negative dCm by dCl. So, the slope of Cm versus Cl curve should be negative to obtain longitudinal static stability. To know the contribution of aircraft components to the pitching moment and hence the static stability of airplane, we will start to break down the airplane into its basic components. We shall develop simple methods for computing the aerodynamic stability and control coefficients. These methods, in general, are accurate for preliminary design purposes and show the relationship between the stability coefficients and the geometric and aerodynamic characteristics of the airplane. Moreover, the presented methods are valid only for the subsonic flight regime. In order to discuss the wing contribution, we have replaced the wing by its mean aerodynamic chord, C bar. The horizontal line is the fuselage reference line, which is usually referred by FRL. The aerodynamic center of the wing is usually located at the quarter chord. The center of gravity of the whole airplane is usually located at ZCG, a distance from the fuselage reference line. The distances from the wing leading edge to the aerodynamic center and to the CG of the whole aircraft are denoted as XAC and XCG. The angle the wing chord line makes with the fuselage reference line is denoted as IW. This is the incidence angle at which the wing is mounted onto the fuselage. The angle of attack, alpha W, is the angle between the wing mean chord line and the free stream wing. The lift and drag are located at the aerodynamic center of the wing. The lift is perpendicular to the free stream velocity, and the drag is opposite to that velocity. The pitching moment is denoted as MAC wing. The source of this moment is that lift was originally generated as a center of pressure without any moments, but the center of pressure is a moving point with the angle of attack. So it is not a good point to be reference. So the lift was translated to the aerodynamic center as a new reference point with the same force and a new moment, which is MACW. The advantage of this translation is to obtain a pitching moment, MACW wing, independent of the angle of attack. Since the whole airplane is considered as a rigid body in this analysis, it is convenient to take moment about the CG of the airplane. If we sum up the moments coming from the vertical and horizontal components of the lift and drag forces, and the pitching moment of the wing about the center of the gravity of the whole airplane. First, the moment of the vertical component of the lift. This is the lift force times cosine the angle between the lift and the vertical, which is the same angle between fuselage reference line and the free stream velocity, denoted as alpha FRL. Which is from geometry equals alpha wing minus the incidence angle of the wing, IW. Times the arm of the force, which is the distance between the aerodynamic center of the wing and the CG of the airplane, XCG minus XAC. Note that the reference point of all horizontal distances is the leading edge of the wing. The second term is the moment of the vertical component of drag force about the CG of the airplane. Since the lift and drag are perpendicular, the cosine will be converted into sine and the same moment arm XCG minus XAC. The third and fourth terms are the moments of the horizontal components of the lift and drag forces respectively. Just note that the moment arm is in this case is ZCG, the distance between the FRL, fuselage reference line, and the CG of the airplane. The last term is the wing pitching moment, MAC wing. Usually, we are not interested in moments as they may vary from one airplane to another. We are interested in the coefficient of moment, which can be obtained by dividing moment by half rho v square SC bar. Take care that the reference dynamic pressure of the whole airplane is the dynamic pressure of the wing. Also, the characteristic length of the longitudinal analysis of the airplane is the mean chord of the wing, which is C bar. So, when dividing MCG wing with this quantity, we get coefficient of moment CMCG wing. When dividing the first term by the same quantity, the wing lift coefficient will appear. XCG and XAC both will be divided by C bar. Similarly, the second term will result in wing drag coefficient. The third and fourth terms can be obtained similarly. When dividing the pitching moment of the wing by the same quantity, it will lead to the pitching moment coefficient of the wing about the aerodynamic center of the wing CMAC wing. Since we are in a preliminary stage, we are not interested in a very accurate analysis. This is because we have dozens of alternatives and choices to design our airplane. So, the equation of moment coefficient can be simplified by assuming that the angle of attack is small. And hence, the following assumptions are valid. Cosine small angles is equal to 1. Sine small angles is equal to the angles themselves in radians. Moreover, usually CL is much greater than CD. So, in this equation, the second term could be neglected with respect to the first term. The third and fourth terms, which represent the horizontal components of the forces, can also be neglected due to their small moment arm ZCG. Hence, the wing contribution to the pitching moment coefficient can be reduced to these two terms only. So, the contribution of the wing to the whole pitching moment of the aircraft is only by the lift force and the pitching moment of the wing about its aerodynamic center. As we know from aerodynamics that the coefficient of lift of any cambered wing is equal to CL0 plus CL alpha times alpha, plugging this equation in the last obtained one, we get the following expression. Our objective is to isolate the constant term from the variable term with alpha, to put it in the form Cm0 wing plus Cm alpha wing times alpha. By simple algebra, we can find that Cm0 wing equals to Cm AC wing plus CL naught wing times this term, and CM alpha wing is equal to CL alpha wing times the same term. The contribution of the wing to Cm alpha of the whole airplane will be by this term. It is obvious that CL alpha wing is usually positive, and the CG of most conventional airplanes lies behind the aerodynamic center of the wing. Hence, this bracket is also positive. So Cm alpha will be positive. Let's recall the condition of longitudinal static stability of the aircraft. Cm alpha should be less than 0. So this term is destabilizing the airplane. On the other hand, the constant term Cm0 wing equals CMAC wing, which is usually negative and usually greater in magnitude than the second term. Finally, Cm0 wing is a negative quantity. Let's recall the second condition of longitudinal static stability of the airplane. Cm naught should be positive, should be greater than 0. So this term is destabilizing the airplane too. Therefore, the wing contribution to longitudinal static stability is destabilizing for most conventional airplanes. From an aerodynamic point of view, the tail is like the wing, as it is a wing-like shaped 3D surface. However, the main function of the tail is to sustain stability. That's why we call it a tail, like birds. The wing is usually cambered to generate lift, however, the tail is usually symmetric. Since the cross-section of the tail is usually symmetric, the center of pressure Cb lies on the aerodynamic center at the quarter chord, and hence no pitching moment about the aerodynamic center will be generated by the tail lift force. So the coefficient of moment about the aerodynamic center of the tail is equal to 0. Also, because of symmetry of tail sections, the lift is usually generated by the angle of attack. Moreover, the velocity at the tail is different from that of the wing, as it is subjected to downwash coming from the traveling vortices generated at the tip of the wing. The angle between the free stream velocity vector and the deviated velocity vector at the wing is the downwash angle epsilon. In this analysis, the tail surface will be replaced by its mean aerodynamic chord. The tail is mounted at an incidence angle IT. The free stream velocity vector is shifted by the downwash angle epsilon. The lift and drag forces are assumed to be vertical and horizontal because of the agreed small angles approximation. The aerodynamic center of the tail is located LT distance from the CG of the airplane. This distance will be the arm of the moment generated by the tail lift. The aerodynamic center of the tail is located Z distance from the CG of the airplane. This distance is very small compared to LT, the tail moment arm. Hence, the horizontal component of the forces will be neglected with respect to the vertical component of the forces because they have a very small arm compared to this very long arm. The pitching moment due to the tail can be obtained by summing the moments about the center of gravity. The contribution of drag will be neglected compared to the contribution of the lift. This is because the coefficient of lift is much more bigger than the coefficient of drag. The horizontal components of lift and drag will also be neglected as their moment arm ZCG is much more less than the moment arm of the vertical components of the forces LT. Look here. This is the LT, the moment arm of the horizontal tail, and this is the arm of the vertical component, and this is the small arm of the horizontal component. So you will neglect the horizontal force contributions to the moment compared to the vertical contribution. The pitching moment of the tail about the aerodynamic center is 0, since the tail airfoil is usually symmetric. So only the first term will remain in this equation, which contains the lift force of the tail, L capital T, times the moment arm, L small t, and the cosine function will be approximated to 1 due to small angle approximation. The tail lift Lt is equal to the dynamic pressure of the tail times the area of the tail times the coefficient of the lift of the tail. Substituting this expression back in the last equation, we get the contribution of the tail in the pitching moment about the CG to be minus horizontal tail moment arm, L small t, times coefficient of the lift coefficient of the tail times the dynamic pressure of the tail times the tail area, St. Note that the minus sign is due to the pitching down moment resulted from the tail lift force about the CG of the airplane. We are not interested in moments as they may vary from small to huge airplanes, so we will divide by half rho v square, which is the dynamic pressure of the wing, times S, which is the area of the wing, times c bar, which is the characteristic length of the airplane, which is the mean aerodynamic chord. Note that the reference dynamic pressure is the dynamic pressure of the wing, and the reference length in longitudinal analysis is the mean aerodynamic chord of the wing c bar. Let's define a new dimensionless quantity, the ratio between the dynamic pressure of the tail and that of wing. We will call it tail efficiency, eta. The magnitude of this eta depends on the location of the tail. If the tail is located in the wake region of the wing, eta will be less than unity. If the tail is located in the slipstream of the propeller or in the exhaust wake of the jet engine, it will be greater than unity. In general, it can have values in the range between 0.8 to 1.2. Let's define another dimensionless quantity, which is the horizontal tail volume ratio, VH. It is equal to the tail moment R times tail area divided by the wing area times the characteristic length c bar. Substituting back into the pitching moment equation, after being divided by this quantity, we will end up with the pitching moment coefficient of the tail about the CG of the whole airplane is equal to minus the tail volume ratio times the tail efficiency times the tail lift coefficient. This tail lift coefficient is usually equal to CL naught tail plus CL alpha tail times alpha tail. CL naught tail is usually equal to 0 due to the symmetry of the cross section of the tail. Finally, we get this expression, which includes alpha tail, which should be correlated to alpha wing later on. As discussed before, the downwash angle epsilon is the angle between the free stream wind and the deviated wind Vt that will reach the tail. Let's define the angle x to be between the fuselage reference line FRL and the direction of Vt. Both of these angles are equal because they are alternate interior angles. From a geometry point of view, the angle of attack of the tail alpha t is equal to the incidence angle of the wing plus this angle x. And this x angle plus the downwash angle are equal to alpha FRL because they are all also alternate interior angles. This alpha FRL from the geometry, it is equal to alpha wing minus the incidence angle of the wing, IW. Substituting back with the last two equations into the angle of attack of the wing, alpha t, we get the angle of attack of the tail as a function in alpha wing, the angle of attack of the wing. Now, what about the downwash angle, epsilon, and how it is related to the angle of attack, alpha w? It can be derived from finite wing theory behind a wing with an elliptic lift distribution to be a function of the lift coefficient of the wing, CL wing, and the aspect ratio of the wing, ARW, as shown in this expression. Since CLW is equal CL node W plus CL alpha W times alpha W, the downwash angle could be written in a more convenient linear form as follows. The constant part, epsilon naught, will be function of CL node W which is not zero for a cambered wing because we are talking about the coefficient of lift of the W, which is wing. The variable part, d epsilon by d alpha, will be a function of CL alpha W, as shown in this expression. Back to the contribution of the tail to pitching moment about the CG of the airplane. Substituting with alpha tail and the downwash angle as derived previously, then when trying to collect the constant term away from the variable term so as to get the contribution in a form of a linear equation, note that alpha in this equation is alpha wing. Whenever we say alpha without a subscript, we mean alpha of the wing. It is the reference alpha for the whole airplane. We get CMCG note, the constant term, is equal to eta times VH, which is the volume ratio of the horizontal tail, times the coefficient of the lift of the horizontal tail, CL alpha t, times the constant part of alpha t. Take care of sign change due to the minus sign in the original equation. On the other hand, the slope of the linear equation, Cm alpha t, will be the expression which was multiplied with alpha in this expression. Recalling the conditions of longitudinal static stability of the whole airplane, Cm alpha should be negative and Cm naught should be positive. Fortunately, Cm alpha tail is a negative quantity, as d epsilon by d alpha is in the range of 0.4, so this bracket will be positive, and the tail efficiency, the tail volume ratio, and the coefficient of lift of the tail are always positive quantities, so the whole expression will be negative. As to Cm naught, these are positive quantities, and the incidence angle of the wing is usually positive, and the epsilon naught also is usually positive. So we can adjust the incidence angle of the tail, IT, to make this term positive enough to trim the airplane at a positive angle of attack. Sometimes the wing is mounted at a negative incidence angle to get a desired positive intercept Cm naught. So the tail is used to stabilize the airplane through this negative Cm alpha tail, and it is used also to let the airplane fly at a positive angle of attack to generate lift through the positive Cm naught of the tail. The contribution of Cm alpha tail will become more negative by increasing the tail volume ratio through increasing the tail moment arm, LT, or tail area, ST. Also, the negative quantity can be increased by increasing the coefficient of lift of the wing, CL alpha tail, and this can be done by increasing the aspect ratio of the tail plane 4. Theoretically, the designer can choose any of these parameters to adjust the slope of Cm alpha. However, in practice, the only parameter making up the volume ratio that can be varied by the stability and control designer is the horizontal tail surface area, ST. The other parameters are related to the performance specifications of the airplane.